Good morning, everyone. And for those who slept in rather than attend the keynote, welcome to day 2 of Astracon. As Jared said, I'm Alistair Cunningham, founder and general manager of Integrics. This morning, I'm going to be talking to you about best practices for reliable carrier-grade telephony. There will be a presentation of between 15 and 20 minutes, and a question and answer session after that. As some of you may know, we're the creators of NSwitch, which is a soft switch built on Asterisk, OpenSIPs, and other components for carrier services such as hosted PBX, ITSP, SIP trunking, and so forth. The information in this presentation has been derived from supporting NSwitch systems over the last 7 years, and before that, from supporting IBM's voice systems worldwide, up to 24 million users. Users of telephony systems have extremely high expectations of reliability based on their expectations and experiences with the PSTN over the last few decades. How do we reproduce that in a modern telephony environment such as voice over IP? For that matter, how do we achieve high reliability in any mission-critical IT system, such as web or email? Well, technology is important, and we'll talk about technology in a moment, but people and culture are even more important. Our principal enemy when trying to achieve reliability is complexity. This is primarily due to the very large number of interacting components in a modern telephony system. We have 2 tools at our disposal to fight complexity. The first is to reduce the complexity itself, and this should always be our first port of call. The other is discipline. Discipline is a key part of corporate culture. It must permeate the entire organization. It must start with senior non-technical management. Senior management needs to prioritize the reliable running of production systems. They must lead by example, and they must not adopt an attitude of do as I say, not as I do. Management needs to foster a culture of open discussion, where the most junior person in the organization can propose improvements and know that they will be seriously considered. They also need to make sure that people can feel that they can admit their mistakes without fear of punishment, and that these mistakes are openly discussed, learned from, so that they can be avoided in future. Complexity is most apparent when upgrading systems or making changes to them. As I said, this is primarily due to the large number of interacting components. This interaction means that risk is inherently unpredictable. It's hard to know which particular change in a change set will cause problems, but we do know that risk is cumulative as more and more changes are made to a system. A large number of small changes, which are casually accepted, tend to produce higher risk over the long term than a small number of large intrusive changes which have been carefully considered, carefully planned, and carefully tested. To reiterate that point, because it's so important, it is the casual acceptance of many small risks that is the most dangerous thing an engineer can do. It's therefore vital to test all changes on a staging system before putting them on production. The staging environment needs to mimic production as closely as possible. If the production system is a cluster, and we'll be talking about that in a moment, the staging system should ideally be as well. Naturally, it must run the same software versions, configurations, customizations, and if at all possible, be loaded with real-world customer data. It's important to keep records of all changes. This is not so that blame can be assigned should something go wrong. Indeed, it's important to avoid assigning blame wherever possible. Assigning blame doesn't prevent people from making mistakes. It merely encourages them to cover the mistakes they make so that the organization can never learn from them. No, instead, the purpose of keeping records of changes is to encourage people to carefully consider and plan changes before they're made. It's beneficial to have some form of change management system, even if it's just a wiki. It's a good idea to keep customizations to a reasonable minimum. This minimizes the chances of encountering a scenario that the designers of the system couldn't have anticipated and haven't tested. So who's responsible for doing this? Well, it's important that every production system have an individual person with explicit responsibility for maintaining that system. Without such a person, you can have no expectations that a system will be maintained coherently or even maintained at all. This person typically cannot be non-technical management. Senior management has many other responsibilities and generally doesn't have the technical skills. This person needs to have a good high-level understanding of all the components that comprise the system and what other systems it interacts with. They do not need to have a detailed technical knowledge of every component that comprises the system, and it's perfectly acceptable for them to delegate work to others. This person needs to have sufficient political influence within the organization. If another department, such as sales and marketing, demands changes to the system that would do more harm than good, the system owner must be able to push back. Of course, this does not give them an excuse to impede progress. The balancing of the competing demands of progress on the one hand and stability on the other hand is something that the system manager needs to be aware of, and mastering this is an art that every engineer and every manager of engineers needs to acquire. What happens if you're running a software package which is produced by an external vendor or by contractors with whom you have a close relationship? Vendors and contractors can never take the place of your system manager. This role must be kept in-house. Vendors, of course, have a detailed knowledge of their own products, but they can never know the environment in which you run it as well as your staff do. They don't know what other systems you have interacting with it. They don't know what customizations you've made. It's therefore a good idea to give vendors access to a staging machine, but not to the production machines. Whenever the vendor produces a new version, if they have a close relationship with you, they can put it on the staging machine there, test it with your configuration and your customizations. Your staff can then do acceptance testing before putting it on production. Since your staff are the only people with access to production machines, it's vital that they have good debugging skills. Should a problem occur on production, they need to be able to solve it there and quickly, or at very least provide a meaningful bug report to the vendor. It's important to keep up with critical information and critical updates from the vendor. in particular security updates from your operating system vendor. So we've talked a little bit about people, and we've talked a little bit about culture. Now let's talk a little bit about technology. As we all know, hardware and software can and does fail. When this happens, we need to continue service. This generally means duplicating functionality, and this leads us to a cluster architecture. It's important to duplicate all critical functions within the cluster. Since this is Astracon, you'll probably have multiple asterisk machines processing calls. You may want some form of SIP proxy in front of them, taking inbound calls and distributing them across the asterisk machine. There are various products to do this, and if anyone is interested in this, I suggest you go to Alipay's talk this afternoon on OpenSIPs and Camelio, which are two of the leading products in this area. You'll probably want some form of database holding customer configuration, billing records, and so forth. So typically you'll have a pair of database machines with replication and some form of heartbeat failover between them. You may want to do the same for file storage. You may want to split the cluster across multiple locations with half the cluster at one site and half the cluster at another. This does impose some fairly stringent requirements on the design of the cluster, in particular the network used to connect the cluster together. And if anyone is interested in discussing that, I'd be happy to take questions at the end of this presentation. Remember to duplicate utilities, such as power, network, and air conditioning. When designing the cluster, it's important to consider the extra complexity that this introduces. There is no perfect cluster design. Every cluster is a compromise between, on the one hand, adding more machines for extra duplication and extra scalability, and on the other hand, keeping the cluster as simple as possible to avoid complexity. There's no point at all in having a cluster which fails over to a backup server in the middle of the night, only to find that clients won't connect because it's running an older version of your software, for example. This means overall that clusters can solve many failure modes, but they do introduce some of their own, and these need to be carefully considered. This is primarily a matter of experience, but careful planning and careful testing can help. It's vital to maintain consistency between machines in the cluster. For example, the failover example I just quoted above. Software versions are particularly important, but so is configuration and customization. You may want to do what we do in NSwitch and store as much configuration and customization data as possible within the database so that it's automatically available to all machines within the cluster. I'm frequently asked whether virtual machines are a good idea or not. And for busy production systems, I generally say no. Now, people in other presentations who work with virtualization will no doubt sing its praises, and I agree it has many advantages, such as flexibility. Unfortunately, in the real world, in my experience, virtual machines tend to suffer more outages than physical machines. Partially, this is technical because of the extra layer of complexity that virtual machines introduce. Partially, it's cultural. Staff tend to treat virtual machines with a lower level of respect than physical machines. They tend to treat them as somewhat disposable. This is unfortunate, but it happens. It's vital to monitor all resources within the cluster, CPU, memory, power, network, air conditioning, and most importantly of all, disk space. Disk space is the most critical because it's durable. It doesn't decrease when system load decreases, and log files can gradually, or even rapidly, fill up a file system and strangle a machine. Naturally, you'll want to take backups of the cluster. It's a good idea to take nightly backups and store them off-site of all fast-changing data, such as customer configuration and billing records. It's also a good idea to take monthly backups of system configuration files, and again, before and after any major upgrades. In the real world, what actually causes outages? Well, real-world outages tend to be one of a few root causes. Firstly, untested changes being made to machines, and we've talked a little bit about the need for planning and testing. Secondly, hard disks filling up, and we've talked about the importance of monitoring. And thirdly, power and network outages, and we've talked about the importance of duplicating these, and we've touched a little bit upon spreading them across locations. The good news is that if you can avoid these three root causes, that's sufficient to avoid the majority of outages in a real-world environment and achieve good reliability. That concludes the presentation. Do we have any questions? Yes?
You've got your list of three things that cause reliability, but what about external events like hackers, customers, and things that might be unpredictable things to your system?
That's absolutely true, and a very good point. You will want to put procedures in place to avoid hack attacks, and I'm sure, as many people know, this year has been particularly difficult for that due to the release of SIP-Vicious at the start of this year. Password security on SIP accounts is, of course, key. It's also highly beneficial to do some form of IP address checking, fail to ban, easy sysadmin, products like that, which detect large numbers of packets from a particular source IP address and bans that IP address for a time. It's also important to have some form of loop detection within the telephony software. Customers do occasionally configure loops within their call routing, and it's important to detect and break out of loops when this happens. Yes?
I've got a microphone here. Let's use that, pass that around so people can hear the question better.
In the IP world, we have BGP for peering. In the SIP world, is there anything on the horizon, or is there anything going between carriers? It's not necessarily sufficient, especially if you're with Asterisk integrating with the various carriers. Some of the higher level carriers don't work with Asterisk, or they don't. There's no certification for Asterisk. So you're dealing with second tier carriers for SIP, for your SIP trunks, and how do we, I mean, where are we going with that with regards to some type of protocol that would allow for SIP failover? Number registrations, really.
Of course. So the SIP protocol itself doesn't have very much for that. The PSTN in some countries has a BGP-like structure for propagating numbers and the routing towards numbers through the PSTN in that country, but that's by no means universal. But we as telephony providers can do various things to improve failover between carriers. Firstly, of course, Asterisk has the Qualify facility where it can regularly ping out to the gateways of the carriers that we're connecting to, and we can configure failover within the Asterisk dial plan, or if we're using some higher level application within its routing logic. But the SIP protocol itself, not so much. But of course, SIP does depend completely on the underlying IP network, and there are various ways of doing failover at the IP level as well. I touched briefly upon heartbeat within a cluster architecture, so you can have a pair of machines, primary and backup, with an IP address that primarily runs on the main machine, and the backup machine monitors the health of the primary machine at all times. Should the primary machine go down or have a problem, the backup machine can then configure that IP address and maintain service. It's also, of course, possible to do just plain BGP. For example, you could have a cluster split across two locations, both of which are advertising a BGP route to the internet for your services. And if one site goes down, then IP traffic will be routed to the other. Yes?
Thank you. You mentioned earlier in the talk about the distributing components of a cluster just geographically.
Yes.
And you mentioned can you comment on the types of network setups you can have between two sites that'll work, and the characteristics of how reliable you can make that cluster if it is geographically dispersed?
Indeed, yes. So it is, of course, advantageous to spread a cluster between two sites to avoid suffering an outage should one site entirely go down. There are both advantages and disadvantages to this, though. The advantage is, of course, as I said, if a site goes down, you continue service. The disadvantage is that there's quite a lot of extra complexity involved, and this complexity can cause some problems on its own. So this is really only something you would want to do if you have a high level of confidence in your staff's ability to manage complex networks across multiple sites. In terms of what architecture to use, there are a number of different layers at which the failover between sites can happen. The first and simplest is at the network layer. If you can present a single network to the applications that is spread across both locations with a single IP subnet, with some IP addresses at one site and some at another, yet which are accessible from everywhere it needs to be accessible from, this is the simplest way from the application level. The application just sees a single network and doesn't need to worry about failover. The other alternative is to do the failover at the application level. If you have a database server at each site with replication between them, each telephony machine can then access its local database. But at that point, you need some form of failover for the telephony coming into the system. This is generally possible for SIP phones using DNS SRV, or perhaps even just backup registrars in handsets. It tends to be a little bit more problematic for DID providers, for example, to get calls in from the PSTN. Some DID providers support registration, so your telephony servers can register out to their servers and they'll deliver to whatever machines they have. But not all do this, and there are also some disadvantages of doing this. It tends to be that the larger carriers tend to deprecate this for scalability purposes on their sides. So there's no perfect answer. It is really a question of talking to your hosting provider or multiple hosting providers, possibly gaining your own AS, so you can do your own BGP network and fail that over between sites can help. But there's no correct answer to this problem. Yes?
I wanted to ask about cold spares versus hot spares. And so in order to maintain configuration consistency and proper respect for the systems that are acting as redundancy systems, we like to leave them all up. However, there's a downside to that, in which case, if you're going to run out of disk space on one and they're load balanced 50-50, you're going to run out of disk space on both of them at the same time, or other things like that. Whatever's eating up all the RAM will eat up the RAM on all the systems at the same time. So it's like, what's the overall, your view from experience? Should we go through the effort of making a cold spare to have as a failover system, or keep going all systems up at all times?
Thank you. This is a topic that I have strong feelings on. I strongly dislike cold spares for exactly the reason that you've talked about. When the system is first installed, the cold spares are, of course, installed and configured in exactly the same way. 3 months later, they've probably still been updated and they're nice and consistent. A year later, they're probably a little bit out of date and running older versions. Maybe they haven't been tested for 3 months. 2 years later, they're hideously out of date. They're running a version of software that no longer even loads the database. Their configuration is nothing like the production machines. They're worse than useless. They introduce complacency without having any technical benefits. In my opinion, all machines should be running as much of the time as possible and should be updated as much as possible. Now, of course, just because a machine is running doesn't mean that it needs to be active. It's perfectly acceptable to have a hot spare as long as it's fully part of the cluster and fully maintained as part of the cluster. It's perfectly acceptable to keep it running, but with no traffic on it. This also, of course, has the advantage that you can configure some form of automatic failover to it should the primary machine go down in the middle of the night. Yes, right at the back.
Because these are production systems a lot of the time, what processes, what protocols do you put in place to actually test the automatic failovers?
Yes, this is very important. Firstly, of course, you'll want to have a staging system which mimics production as closely as possible, including the ability to do failovers in exactly the same way as production, so you can test your configuration and new versions of the failover software there. But inevitably, you do need to test failovers on production in real life. There is no magic bullet to do this. You just need to do a failover on production. You will, of course, choose the quietest time, such as 4 a.m. on Sunday morning. But you do need to schedule this for regular occurrences. Once a month, once every 3 months is probably acceptable, but I wouldn't recommend any longer than that.
One question about keep track of changes. How do you suggest to keep track of changes? Using like Subversion or Git on the config files or what?
Yes, so for configuration files, Subversion or Git or something like that is very beneficial, and Puppet is a good way to roll it out across machines. An alternative, which is what we do as much as possible, is store configuration in a database, which is then accessible to all systems in the cluster. But there's an additional level of keeping track of changes which you'll want to do as well, which is more at the human level in terms of documentation. There are various tracking systems for this. Personally, I just like a wiki. It works well. Whenever you make a change, just add a note to the bottom of the wiki page.
Any other questions? Now's your chance.
Okay, excellent. Well, thank you very much for attending, everyone. It's been a pleasure to speak to you today. Thank you.